For 20 years, Florida had a problem. Its oysters were dying. Its coastlines were crumbling. And in the middle of this crisis, the state made a strange choice. Instead of throwing away 500,000 tons of used oyster shells, they dumped them back into the sea. What happened next surprised even the scientists who planned it. This is the story of how waste became a living wall against the ocean. Florida's water was changing, slowly, quietly, and almost without anyone noticing. Beneath the surface of its bays and estuaries, something ancient was disappearing. Oyster reefs had lined these waters for thousands of years. They were not just clusters of shellfish. They were structures, living walls built layer by layer, generation by generation, each oyster settling on the shell of the one before it. These reefs filtered the water. They broke the force of waves. They gave shelter to fish, crabs, and countless smaller creatures that depended on their rough, uneven surfaces to survive. But by the early 2000s, something had gone wrong. Across the Gulf Coast, oyster populations had dropped by more than 80% from their historic numbers. In some bays, the decline was even steeper. Reefs that once rose in thick clusters near the shoreline had been reduced to scattered, broken fragments. The causes were not a single dramatic event. They built up slowly, like sediment settling on a riverbed. Decades of overharvesting had stripped shell material faster than nature could replace it. Industrial runoff and storm damage disrupted the delicate mix of salt and fresh water that oysters needed to survive. Then came the disasters people did notice. The Deepwater Horizon oil spill in 2010 devastated marine habitats across the Gulf. Hurricanes battered the coast again and again, burying reefs under shifting sand and silt. By 2020, the damage in some areas had become impossible to ignore. Apalachicola Bay, once one of the most productive oyster fisheries in the entire country, saw its wild harvest collapse so severely that regulators shut it down completely. A 5-year closure, an entire industry paused, waiting for the water to heal. For coastal communities, this was not just an environmental story. It was economic. It was cultural. Oyster harvesting had shaped towns along Florida's coast for generations. Families had built their lives around these waters. Restaurants had built their menus around these shells. And now, the shells themselves were vanishing. But there was a deeper problem hiding beneath the obvious one. Oysters need something hard to grow on. Baby oysters, cold spat, cannot simply float and settle on soft mud or sand. They need calcium carbonate. They need old shell. Without reefs, there was nowhere for the next generation to attach and grow. It was a cycle with no easy exit. Fewer live oysters meant fewer shells. Fewer shells meant less surface for new oysters to settle on. And less new growth meant the reefs kept shrinking. Year after year, with no sign of recovery, scientists watched this unfold with growing concern. They understood the mechanics of the problem. They even understood, in theory, what needed to happen to reverse it. What they did not yet know was whether anyone would be willing to try something as strange, as expensive, and as unproven as what came next. Because the solution being discussed in quiet meetings across Florida's environmental agencies was not going to look like an act of restoration. To most people watching from the shore, it was going to look exactly like an act of destruction. If you value deep investigations like this, consider subscribing. The idea sounded almost backwards. If oyster reefs were dying because there was not enough hard shell in the water, then the answer was simple. Put shell back. Not new shell. Not manufactured material. The very same shells that restaurants and seafood processors were already throwing away by the ton. Every single day, across the Gulf Coast, oyster shucking produced an enormous amount of waste. Restaurants served oysters by the dozen. Processing plants shelled them by the truckload. And almost all of that shell ended up in landfills, buried and forgotten, treated as garbage rather than as the exact material the ocean desperately needed. Restoration groups had noticed this waste for years. Small recycling programs began popping up in scattered pockets along the coast. Restaurants were asked to save their shells instead of throwing them out. Volunteers collected buckets of shell from kitchens and hauled them to collection sites. It started small, a few tons here, a few tons there, but small was not going to be enough. The scale of the reef collapse demanded something far bigger than volunteer buckets and weekend cleanups. So the plan grew. Government agencies, universities, and conservation groups began coordinating on a much larger scale. Programs across Florida, Louisiana, Alabama, and Texas started collecting shell in far greater volumes, curing it properly, and preparing it for return to the water. Funding began flowing in from federal sources, aimed at rebuilding what decades of decline had taken away. The process itself was slow and deliberate, even if the ambition behind it was massive. Collected shells could not simply be scooped up and dumped straight into the bay. They had to be cured first, left outdoors for months, so that natural elements and scavengers could clean away leftover tissue and reduce the risk of introducing bacteria into the water. In Florida, this curing process took a minimum of 3 months. In colder regions, it could take twice as long. Once cured, the shell was ready. It was loaded onto barges, or carried out by volunteers in bags and rings and containers, and lowered into carefully chosen locations. Sites where oyster reefs once thrived. Sites with the right mix of salinity, water flow, and depth to give new growth its best chance. Over time, this effort scaled into something extraordinary. Collectively, recycling programs across the Gulf region had returned millions of tons of shell to coastal waters. In Florida alone, contributions from state agencies, conservation groups, and volunteer partnerships added up year after year. Project after project, reef after reef, to an outsider watching a barge unload tons of broken shell into open water. It might have looked chaotic, wasteful, even, shells scattering across the seafloor in what seemed like a haphazard pile. But every location had been chosen with purpose. Every curing schedule had been followed with precision. This was not dumping in the careless sense of the word. It was engineering, disguised as waste disposal. What nobody could say for certain, not yet, was how the ocean would respond. Reef restoration had worked on smaller scales before, but projects of this size, across this much of Florida's coastline, had never fully been tested. The shells were in the water. Now came the hardest part, waiting to see if the ocean would remember what to do with them. The waiting was the hardest part for everyone involved. Scientists could plan a reef. They could choose the perfect location, cure the shell correctly, and lower it into place with careful precision. But once it settled on the seafloor, the outcome was no longer entirely in their hands. Nature had to take over. In the days immediately following deployment, the shell piles looked lifeless, just broken white and gray fragments scattered across brown sediment. To the untrained eye, nothing seemed different from any other patch of ocean floor. But underwater, at a scale too small for human eyes to notice, something had already begun. Within hours, microscopic organisms started arriving. Bacteria settled onto the rough surfaces of the shells. Algae followed soon after, forming thin, slippery films across the calcium carbonate. Scientists call this a biofilm, and it is one of the most important early steps in reef formation. This film is not simply passive residue. It actively changes the chemistry of the surrounding water. It sends out chemical signals, invisible cues that travel through the current and reach the larvae of oysters and other marine creatures drifting nearby. For oyster larvae in particular, these signals act almost like an invitation. Oyster spat are naturally drawn to calcium carbonate surfaces. It is embedded in their biology, a survival instinct passed down through countless generations. When free-floating larvae detect the chemical signature of a biofilm-covered shell, many of them respond by attaching and beginning their transformation into stationary, shell-building oysters. This recruitment stage, as researchers call it, is well documented in restoration science. What made these particular sites remarkable was the density of shell packed into small areas. A single scattered shell might attract a handful of larvae. A concentrated field of hundreds of tons created something far more powerful. It gave larvae an enormous target, dramatically increasing the odds that a wandering, microscopic organism would find a place to settle and survive. Divers and researchers monitoring the sites began to notice changes within weeks. Barnacles appeared first in some areas, small white cones clinging tightly to the shell surfaces. Tube worms followed, building thin, calcified tunnels across the debris, and scattered among them, almost too small to notice at first, were tiny juvenile oysters. New life, attached to the remains of oysters that had come before. It was a strange kind of continuity. The shells of oysters long dead were now serving as the foundation for oysters not yet fully formed. Death and growth intertwined in the same structure. For the scientists watching closely, these early signs mattered enormously. They confirmed that the underlying theory was sound. The chemistry worked. The biology worked. The larvae were responding exactly as decades of research had predicted they should. But early colonization was only the beginning. A handful of barnacles and juvenile oysters did not yet make a reef. What mattered now was whether this fragile new growth could survive its first storms, its first predators, its first true test against the unpredictable forces of the open water. The shells had done their job in offering a foundation. The question that remained was whether life, once given a chance, would choose to stay. If you value deep investigations like this, consider subscribing. 4. Built from trash, not stone, there is something almost poetic about what was happening beneath the surface. Material that had once been considered garbage, scraped off dinner plates and swept out of restaurant kitchens, was now forming the skeleton of a living structure. Calcium carbonate is calcium carbonate. To the ocean, it does not matter whether a shell came from a wild oyster harvested a century ago or from a plate served at a seafood restaurant last week. The chemistry is identical. The structure is identical. And that simple fact is what made this entire approach possible. For years, conservationists had debated the best materials for reef restoration. Some experimented with concrete structures, engineered specifically to mimic natural reef shapes. Others tried limestone boulders or purpose-built domes designed to attract marine life. These materials had their uses, but none of them carried the same biological signature as real oyster shell. None of them spoke the same chemical language that oyster larvae had evolved to recognize. Recycled shell offered something artificial materials simply could not replicate. Authenticity, a texture and chemical composition that matched exactly what wild oyster spat was searching for. This is why the recycling programs mattered so much. Every restaurant that saved its shells instead of throwing them away was contributing raw material for reef construction. Every volunteer who hauled buckets to a curing site was participating in something larger than themselves. A supply chain, once linear and wasteful, was slowly being transformed into something closed and regenerative. Shells were harvested, consumed, discarded, collected, cured, and returned to the water where new life could use them again. Program directors involved in these efforts often described the old system in blunt terms. The supply chain had been extractive. Shells moved in one direction only, from ocean to plate to landfill, with nothing ever returning to where it came from. The new approach closed that loop entirely, as more of these recycled shells settled onto the seafloor and began attracting new growth. Researchers noticed the structures taking on a distinct architecture. Layers began to form. Older shell provided a base. New oysters attached on top, growing outward and upward as each generation added to the one before it. This layering is critical to how natural oyster reefs function. It is not simply a pile of shell. It becomes a three-dimensional structure with crevices, gaps, and elevated surfaces that create countless microhabitats. Small fish could hide in the gaps between shells. Crabs could burrow into softer sediment, protected by the reef's overhanging structure. The complexity of the reef, its uneven and irregular shape, was exactly what made it valuable to so many different species. What had begun as a flat scattering of waste material was slowly transforming into something with genuine architectural complexity. Height, texture, shelter, and this transformation revealed something important about restoration itself. Rebuilding a damaged ecosystem did not always require inventing something new. Sometimes it simply required returning what had been taken away. and trusting that the underlying biological processes still remembered how to build. The shells were rising now, slowly, from the seafloor, but rising into what? Exactly, remained to be seen, because a structure is not the same thing as an ecosystem, and what happened next would determine whether this reef became something temporary or something permanent. By the time researchers returned for their follow-up surveys, something had shifted. The reef was no longer simply reacting to what scientists had placed there. It had started reacting to itself. This is the part of oyster restoration that researchers describe as most remarkable, and also the most difficult to fully predict. Once a reef reaches a certain point of maturity, it stops depending entirely on outside intervention. It begins to sustain its own growth through a series of interlocking biological processes, each one reinforcing the next. It starts with filtration. A single adult oyster can filter dozens of gallons of water in a single day, pulling in bacteria, algae, and suspended particles as it feeds. Multiply that by thousands of oysters clustered across a reef, and the effect on water quality becomes significant. Cloudy, sediment-heavy water gradually clears. Sunlight, once blocked by suspended particles, begins penetrating deeper into the water column. That change in light matters enormously to nearby ecosystems. Clearer water allows seagrass to grow in areas where it previously could not survive. Seagrass beds, in turn, provide additional shelter and food sources for fish, crabs, and other marine life. What began as a shell pile was now indirectly reshaping the surrounding underwater landscape, extending its influence far beyond the boundaries of the reef itself. Meanwhile, the reef continued its own internal cycle of growth. Mature oysters release larvae into the surrounding current. Some of those larvae drift away and settle elsewhere, but many return to the same biofilm-coated surfaces nearby, drawn by the same chemical cues that attracted the very first colonizers. Generation after generation, the reef expanded outward from its original footprint, growing beyond the exact boundaries where the shell had originally been placed. Researchers monitoring these sites began to describe the reefs using a specific term: self-sustaining. It meant the structure no longer required continuous human input to keep expanding. The biological feedback loop: filtration improving water clarity, clarity supporting seagrass, seagrass supporting biodiversity, biodiversity attracting new colonizers, had become strong enough to carry itself forward. This did not mean the process was fast. Reef development on this scale unfolds over years, not months. Each layer of growth depends on the survival of the layer beneath it. Storms, disease, and shifting water conditions could still set the process back at any stage. Nothing about this recovery was guaranteed to continue indefinitely, but the early trajectory was undeniable. Areas that had been barren seafloor, stripped of structure and life for years, were transforming into complex, three-dimensional habitats capable of supporting an entire community of organisms. For the scientists who had spent years pushing for this kind of large-scale intervention, watching the reef begin to grow independently was a quiet vindication. The theory had held. The chemistry had worked exactly as predicted. And now, the ocean itself had taken over the project, continuing the work with a kind of momentum no team of researchers could have manufactured on their own. But a growing reef attracts more than just oysters. As the structure expanded, it began drawing in creatures that nobody had specifically planned for, guests that arrived on their own, following instincts and signals written into their biology long before Florida ever dumped a single shell into these waters. If you value deep investigations like this, consider subscribing. A reef is never built for just one species. That is something researchers understood in theory long before these Florida sites confirmed it in practice. Oysters may have been the intended foundation, but they were never going to be the only residents. As the shell structures matured, the earliest visitors, barnacles, tube worms, and small crustaceans called amphipods, had already established themselves in the crevices and gaps between shells. These organisms formed the base of something larger, a foundational food web, built directly into the physical architecture of the reef itself. Polychaete worms burrowed into the softer material, accumulating between shell clusters. Small fish began appearing in greater numbers, drawn by the abundance of prey hiding within the reef's uneven surfaces. This was not a coincidence. It was exactly the kind of layered habitat complexity that oyster reefs are known to provide, and exactly why marine biologists refer to oysters as ecosystem engineers. Their presence physically reshapes the environment around them, creating shelter and food sources for species that could not have survived on a flat, featureless seafloor. Within the first year, biodiversity at several monitored sites increased significantly, and where prey populations grow, predators tend to follow. Predatory fish began moving into the area, hunting among the reef's crevices for smaller species sheltering there. This progression mirrored patterns observed in other controlled restoration studies across the Gulf. But seeing it unfold at this scale, across hundreds of tons of recycled shell, gave researchers a level of confirmation that smaller pilot projects simply could not provide. Blue crabs were among the more notable arrivals. These crustaceans benefited directly from the reef's complex structure, using its crevices as protection during vulnerable stages of their life cycle, particularly after molting, when their new shells remain soft and they are especially exposed to predators. The reef's uneven terrain offered exactly the kind of cover they needed to survive these dangerous windows. What emerged was not simply an oyster colony. It was a functioning miniature ecosystem, layered with predator and prey relationships, filter feeders, scavengers, and opportunistic species, all interacting within a structure that, only a short time earlier, had been nothing more than a scattered pile of restaurant waste. For researchers documenting these changes, the presence of so many unplanned species carried real scientific weight. A reef that only supported oysters would suggest a narrow, fragile success. A reef supporting dozens of interconnected species